Hello, Ken. Ken, are you there? Cannot hear you, Ken. If you're speaking or nothing. I hope Yes, I can hear something, but not an audio as such. Can I speak again? Nope. Hello?
Can you hear me?
Yes. Now it's
Okay,
it,
good.
let's see. Harsha. There's homework 3 that I uploaded today. Tuesday again. And midterm. Okay. So we talked about Snell's law last time for stratified medium in the sense we broke the medium into discrete parts. So, this is a quick
Yeah.
overview. Yes, we did a quick, this is a quick overview of what we did last time. So if we have a medium of broken into layers, right, called stratified medium, right? So this is, let's say, N1, N2, N3, and let's say N4. And in principle, you could have many of them. And at the endpoint, light comes out. And at each point, it obeys, at each interface, it obeys Snell's law. But one would like to know, what is this curve? So if you were to break this into smaller and smaller pieces, you can think of a path that would suit light, right? So this will be minimized. The time taken for this path will be minimized. So this is a path with a minimum time. And that's a solution, or if you want, that's a spectral path. And around that, there is all other paths also possible, right? So this is one, this is another one, and so on. It doesn't really have to be all wiggly at all. It could be smooth. Like straight line is another simple function, right? That's also a function. And we would like to know, given an n, so if this was a continuous, so let's say given an I, right? So I is the ith layer. If you are given all the refractive indices, which we want, if in the limit when I is really continuous, we want to say given n as a function of x, let's say, if this was x, right? Given n as a function of x, or given n for each layer, find the function y as a function of x. So this is y now. Or let me make this slightly just to keep the discrete piece also. If we are talking in terms of discrete features, we would say this is y as a function of I, right? Y as a function of 1, 2, 3. So there's special values for y. And if we are thinking of it in continuous variables, we would like to know what is the function y of x. So find the function y of x or the function discrete variables yi for which, in this case, we're talking about time, for which the time is minimum. Is that clear? Any questions there? Interpretation or anything of that sort? Is that clear?
Yeah, it's clear.
Okay. To attend to problems of this kind, we would like to make a very generic methodology. And for that purpose, I'm going to digress completely off and define what is called a functional derivative. So we'll define what is functional derivative. So we would like to discuss this. And to discuss that, let's go back to understanding what a derivative itself is. Right? Let's go back and recall what a simple derivative is. Very trivial, but still. Let's say we have a function, let's say, yeah, x squared, let's say. So let's begin with an example. So example is not for functional derivative. Go back to simple function, and I want to motivate functional derivative with that spirit. So let's say function f of x. Let's say very simple, right? X squared. Yeah, let's make it x cubed. Okay. What's the derivative of this function? It's very simple, but still, like we know, derivative of this function is its total derivative. Doesn't matter whether it's partial or total. So it's the f by the x is equal to 3x squared. Very straightforward. But suppose you forgot this formula. We have used a formula here, right? Oh, x raised to n is n times x raised to n minus 1. How would you go about deriving this 3x squared? Like, what's the process here? Various ways you can think of it, but still.
I think you would when you take the tangent of the min-max local points.
That's a geometric picture. That's correct. Yes, yes. Yeah. So your point is, I think the way you're seeing it, you would plot f of x. This is an x cubed. Excuse me. So this is, let's say, if you're suggesting that we plot f as a function of x. This is x cubed, so this will have this feature in here, and pick an x value, draw a tangent to that. Right? So you would draw a tangent in there and probably measure the angle theta, right? That's the suggestion, correct?
Yes. Yeah.
That's correct. That's surely the way you would imagine the derivative to be. That's good. But let me try to go through a more algebraic way. Okay, so that's surely a visual picture of it. And so another way which is more suitable for seeing functional derivative, it comes as a limit, is let's define, it is how you would have also seen derivative in some form. So derivative df by dx, right, is equal to, it's a limit. So notice what you're doing in this diagram is you would pick, so let me zoom this in. So there is a region somewhere here. This is the point where you want to take the derivative. So this is x. That's your x. Instead, you will go to a slightly closer value, so x plus delta x. Because if you want to draw a tangent or a line, you need 2 points, right? So you will go slightly off from the point x, and that leads to a delta x here, and this will be f of x plus delta x, and this will be f of x itself. And you want to find the difference between that, and then take the limit when this delta x goes to 0, right? That limiting feature can be, that's what bothered people in the initial days, that when you take the limit delta x tends to 0, this is 0, that's also 0. So that seems to suggest that there is a quantity delta 0 over 0 showing up. How can that be well defined? We don't know. We don't know how to divide 0 by 0. That's an undefined quantity. But it turns out that for many functions, you can actually, the derivative is unambiguous. So let's see how that goes about. So you would say, whatever I said pictorially there, you would say this is the vertical component is the difference f of x plus delta x minus f of x, and the denominator is x plus delta x minus x, where x of course cancels out, right? So it's only delta x in the denominator. And you also want to take the limit delta x tends to 0. Right, that's your derivative. If it was x cubed, this would be limit delta x tends to 0 of x plus delta x cubed minus x cubed. So divided by delta x, x plus delta x minus x is delta x itself. So how does it still, one might wonder what happens to the 0 by 0 that was coming up. So let's see in detail why or when does that 0 over 0 not create a problem, or why doesn't it create a problem. That's equal to limit delta x tends to 0, and let me pull out the delta x all the way in the front just to have more space. And x plus delta x cube is x cube plus 3x squared times delta x plus 3x delta x squared, and finally there is delta x cube, and all this minus of x cube. So let's see where is that, or let me still want to write one more step. Limit delta x tends to 0 of, right, notice there is x cube over delta x there plus 3x squared. These are taking delta x inside, plus 3x times delta x plus delta x squared and minus x cubed over delta x. Let's take the, at least for a moment, let's think of each of this term. The first term blows up as delta x tends to 0. Right? This is 1 over the, for a given x, x cube is typically finite as far, unless you're talking about x itself to be infinity. For all finite x, x over delta x in the limit delta x tends to 0, that's infinity. Right? That's a very big number, but the nice part is that that cancels away with this last form. So if not for that cancellation, that term is not comforting. Right? It's very huge. It's infinity. So that cancellation is important, and that happens all the time. If that doesn't happen, then you have to worry about it. Right? That cancellation was crucial. And the second term, notice that delta x cancelled out. So you have to do this before you take the limit. Before you take the limit, this delta, these two delta x cancel out. And the third one of them cancelled out, so it survived delta x, and then delta x squared. Right? Now, if you take the limit, only this term contributes. This is an exact quantity. Notice it's not an approximation. In the limit, this really goes away to 0. Like even if there were as many terms as there are, they will all go to 0 in that limit. So it's an exact limit. So that's 3x squared. Right? That's your answer. So two things happen. You first make a series expansion. The first term, which does not have any delta x, has to cancel out before you take the limit. That subtraction will always do that. And the second term, which apparently has this delta x, in the limit delta x tends to 0, will always give you a finite or 0. I mean, it's a well-defined quantity in the limit. And all other terms will go to 0 exactly. Again, not an approximation. It seems like this is small, but it's not. In the limit delta x tends to 0, that's an exact expression. And that's the key to this idea of derivative. And it avoids this, geometrically speaking, there is this issue right there, the 0 over 0 in that limit. How is that well defined? And that's because of this piece captures. So, okay, any questions on that? It should be just a derivative.
Yeah, no questions.
Okay. So we want to now generalize this, right? We want to do a very similar thing, but in a different setup. We want to make this more formal and if you want, in an infinite dimensional space, because that's how functions are defined. Right? So let's do but intermediate, as an intermediate step, let's actually go to another example. Let's say now, again, another example, I will call it, but again, a familiar example, but maybe not as familiar as one would think. Let's go to vector calculus, but I'm not going to talk about a vector field, like electric field is a vector field, but instead let's talk about a quantity that's dependent on three dimensions, like three-dimensional space, x, y, and z. So let we say we have a vector x. So this is equal to x1 I plus x2 j plus x3 k. The moment I write this, I've chosen a basis, right? That is a I, j, and k. So there's a rectangular basis I'm talking about. And if I restrict myself to that basis, then I can stop writing the I, j, k. It is just repetitive. There is no more information. If I assume that I'm not going to leave that basis forever, then this can be thought of as x1, x2, x3. The vector representation is basis dependent, but if I'm not changing the basis, that's components are the only quantities that's relevant, and then I can even think of this as xi. That I is going from 1, 2, 3. So a vector x in three-dimensional space is completely well defined in terms of three components in a basis, in an orthogonal basis, and we choose that to be the rectangular orthogonal basis. And the components are x1, x2, and x3. So that's your vector. And let's say we have a function of x. What could it be? Temperature, right? Temperature is a function of position. For that matter, any scalar field, like you typically, when something's depend on the whole space, you call it a field, like electric field, magnetic field. So you use the word field. You can say temperature field if you want instead of temperature function. F of x could be. Let's take an example, and let's say this is equal to a dotted with x. Right, that's typical. That's a standard dot product that we have, and a could be a constant. So a does not change with position. So a is a constant. By constant, I mean uniform with respect to position, but that's the only thing we have. If a is also a vector, it will have a1, a2, a3, and this is nothing but a1, x1 plus a2, x2 plus a3, x3. That's an expansion. So immediately say that, oh, this is nothing but summation, right? Summation of I going from 1 to 3, ai xi. And now at this stage, you make an approximation or a notation if you want. And I won't be using it too much, but just for informing you, this is also sometimes written as ai xi itself. This is called the Einstein summation notation. Notice I just dropped the whole summation sign there in going from this step to this step. But then how do I know that this is being summed? The notation will be whenever an index, like there is a subscript, whatever shows up, that's an index. If the index is repeated, that means the idea is that it is summed over. So since I is repeated, under two variables in an expression, then I know that it has to be summed. If it comes alone, then it is not a sum. If it is 3 times, you don't sum it. Right? Typically, it doesn't come 3 times, then this notation doesn't work. If there is a situation where I shows up 3 times, then you want to explicitly write your summation sign. But most often, it comes in as under two indices. In that case, this notation works. It's not necessary. I'm just pointing out that there is a whole algebra you can build in that manner. We come back to our simple function, a dotted with x, right? So that's our simple function, if you want. We want to talk about a derivative. Now, in 3 dimensions, when you're taking a derivative, the reasonably general form is the gradient operator, right? So this is called the gradient operator. You must be familiar with that. So gradient operator is in rectangular coordinates. In general, it doesn't have to be in rectangular coordinates, but in rectangular coordinates, it has this nice feature that this is d by dx1 plus j times d by dx2 plus k times d by dx3. And again, you can drop this ijk, right? If we stick to rectangular coordinates consistently, then this is simply di, right? First you write 3 of them and then just simply say this is di. A partial derivative now, because that could be 3 different variables. And let's ask the question. So we would like to calculate what is the gradient of f. What is the gradient of the function f? So that means we are asking what is gradient of a dotted with x. Okay. And what is that equal to?
A.
A, right, that's correct. That's a correct answer. So this is equal to A. And how do you go about doing that?
You would take you just distribute the partials to the x, the a dot x. I'm sorry.
Good. So that's a good way of doing it. So you would say this is, let's say, index from the notation that we have here. So you would say this is the free index. So this is the I. And I want to give some new indices in here. Notice this is a summation, right? So you would say this is a, let's call it a new index because that is to be summed. This is aj, xj. So notice this is summed now. That's an understanding there. So the I has to act on both. But ai is a constant. So this comes out to be aj. I can come out, bring it outside. So this is dj times x, sorry, di times xj. I times xj. And then you have somehow assumed, since you gave the answer, you know that, oh, these are 9 pieces in here, only 2 of them contribute, so this is delta ij. But let's do that more carefully here. So this gives you ai. So let's do that a little more carefully because I want to generalize this to a function, right? So this is the main idea I'm going to, or I would say, this is the exposition of the main idea. And for that purpose, so let me do this slightly more carefully. So this is aj times dixj. So let's say di, so this gradient, which is a function f, right, that has a component I. Think of, we want to now make this as I here runs from 1 to 3. I want to very quickly make it run on a continuous variable going in an infinite infinitely many pieces in a region, right? So that will be a continuous variable very soon. So this is equal to di times so this is aj xj, just repeating here, and that's aj di xj. But what is that equal to? On the left hand side, I have only one index. On the right hand side, I have two indices. So let me write this as, so let's say d so this is gradient of f, that could be 1, gradient of f2, and gradient of f3. And think of this as a vector. Right? I think that's reasonable. That's equal to, again, I can be 1, 2, 3, but when I is equal to 1, j can be summed over. So if I keep I to be fixed, so then I have a1 d1 x1 plus a2 d1 x2, and I have plus a3. Am I doing this right? Yeah, d1 x3. Writing this explicitly, but hopefully this will help in the what we're doing. This is d2 x1, repeating d2 x2 plus d3 d2 x3, and finally a1 d3 x1 plus a2 d3 x2 plus a3 d3 x3. If you want that whole thing as 3 pieces. All this leads to asking what is d1 x1, what is d1 x2, what is d1 x3, and so on. And let me try to, I think, do I have the space there? Maybe I can. So that asks us, what is this quantity? That is what is playing a role in here. So let's say di xj, I represent it as there are 3 pieces. I can take the 3 pieces, j can take, that's a 9 by 9 matrix. And more explicitly, d1 x1 is nothing but derivative of x with respect to x itself. And this is derivative of x with respect to y, and derivative of, oh no, I should have said x carefully. Let me be a little more careful because I want to keep this notation as such. So this is dx1 with respect to x1, dx1 with respect to x2, which is like y if you want, and dx1 with respect to dx3. And next we have dx2 with respect to x1, dx2 with respect to x1, x2 with respect to x2, and the x3 with respect to x1, x3 with respect to x2, the x3 with respect to x3. Right. Which again we see that in general we have a term here like d by dx I, if you want, of xj. That's what we are talking about. If we are being careful with the indices, there is also a covariant and contravariant piece to this. So I in principle should go up, but we are working in rectangular coordinates, so we don't have to worry about those things. It will be always the same. So what is this quantity? And we would say that, what is this equal to? You would say derivative of x1 with respect to 1 is 1. What is derivative of x1 with respect to x2? And you would say that's 0, right? Because you already saw that this is a delta ij. So this you would say is 0. And why is that? So this is 0, that's 0, that's 0, that's 1, 0, 0, 0, 1. So now let me ask, why is this 0? And It's sort of trivial, probably, but still let's emphasize that because we want to generalize this, right? So the question is, why is the 0 x1 with respect to dx2?
Because x1 doesn't, like it's not a function of x2, it doesn't change with any x2, right? So
That's correct, right? So you would say that x1 and x2 are independent variables here, right? So this, when it comes to the function, depending on the three components, in principle, it was possible that you can imagine a situation where one of the variables depends on the other. But the way we have defined it, there is an implicit assumption that x1, x2, and x3 are three independent variables. Like these are the coordinates representing your space, and all these three coordinates are independent of each other. And when we are taking a differentiation, we are saying that we are talking about the derivative of x1 with respect to x2, keeping one of them constant. So let me go to the, so what we are saying is d by dxi with respect to d by dxj, which is the same as the j xi, that's equal to del ij. And here, this quantity again, this partial derivative, if you go back to our notation, this will be limit delta xj tends to 0 of, let's say delta xi, right, xi, so maybe I should write this as well. This is delta xj. Notice that slight difference. This is partial derivative, and this is a small variation. Right? If you want, this is xi plus delta xi minus of xi. And this is xj plus delta xj minus xj. Right? That's what the meaning of that is. And here, it should be interpreted as this is not a ratio of two small quantities. Here we are saying what is the change in xij in the numerator because of the variation in xj. Right? That's the meaning there. So there's a slight difference earlier when we, a simple function x cubed when we did, that was a ratio of two very small quantities. Here we are saying what is the change in xi due to a change in xj, and in that sense, this is equal to 0. So this is equal to 0 if it is equal to 0. If 0 means, so that implies that xi and xj are independent with respect to each other. Slight clarification there that could be a source of confusion if you want. Right. And with that feature, then our derivatives are straightforward, right? And then you say that, oh, this is equal to delta ij. That's equal to delta ij. And with that, our example comes out very straightforward. A dot with x is equal to just a. Let's do one slightly different example in this case. Let's say f of x is equal to 1 over 1 plus a dotted with x. Like the main piece we have already done, so from that point on we can just do it. Let's say if this is square root, or let me make this slightly different. So this is 1 plus a dotted with x dotted with. So what's the derivative of this? How would you go about doing that? Or gradient of x. F. How do you go about doing gradient of f? Is this still in the board? Yeah. And then we will go to the functional derivative. Okay. Try to quickly do that. Oh, Harsha is here.
Yeah, I'm here. I came a little late though.
Yeah. So we started doing functional derivative. We want to attend to what we did last time the refractive index Snell's law. So we are taking a digression and learning how to take a derivative of a function in a sense.
So this is just follow the chain rule and you'd get the answer, right?
Follow the chain rule, correct? So how we would do that is that, so this is the main idea here. But once we have that, we can use, this will be our first reach here. Before that, I take the gradient of the square root. So, so notice what I'm going to do. And this will come up in functional derivative also. So notice the steps here, even though it is straightforward. Notice that I'm taking a derivative as if I'm taking simple derivative. So this is 1 by 2. Right? So that this is raised to half. I'm purposely doing the simple thing. So this is 1 by 2 times this goes in the denominator, right? So this is 1 plus a dotted with x. Until that, that's normal standard derivative. Once I've done that, now I reach the argument of the square root. And while doing the so I have to take the gradient of the argument of the square root. So this is gradient of the argument of the square root. There is 1 if you want. We can write that 1. Like that. So it's 1 plus a dotted with x. But 1 is a constant. That's not going to contribute. And gradient of a dotted with x, we just already did. Right? So that's a, which we know. So that is, so this is equal to 1 by 2 times the vector a divided by 1 plus a dotted with x. Okay. So once we did this was the main piece. Then rest everything involves doing the same thing and then using chain rule, reach this, and that leads to that. So that's a very similar thing. Now we are going to do this for a new kind of functional. We'll call it functional. So let's. Any questions at this stage?
I have a quick question. The partial del xi, partial del xj.
Mm-hmm.
You made those the delta xi and delta xj. Yeah, and then you made yes. Is that just an outcome of the above relation, like the line above it?
Yes. So no, I'm just clarifying this. So that is okay. So maybe what I'm saying is that I want to connect this with what we did earlier, right? As a limiting process. Let me go back to this, right? So yeah, let me go back to this. Okay. So what do I mean here? Let's say that this is a partial derivative, right? So this is partial derivative. Let me write this as dx1 with respect to dx2. Right? That's one specific example there. This is more specifically, this is an operation, right? That's a derivative of x1. And different, and instead of writing it as the ratio of two quantities, that's a derivative of x1. And the derivative I understand as limit delta x2 going to 0, right? Whatever I'm taking the derivative of, and then should make a change in x1, right? So x1 plus, so x1 I'm assuming is a function of x2, like if it was a function of x2, right? So this will, you will say this is x2 plus delta x2 minus of x1 of x2 divided by x1 plus delta x1 minus of x1, correct? That's how you would do this. But now I can also call this f of x plus delta x minus of f of x as delta of f. Right? That could be a definition, and that's what typically you say. In that case, you would write the numerator as, so you would say this is f plus delta f, right? So this is x2 plus delta x2. So that is, in this case, delta x2 means change in x2 due to a change in x1 minus of x2 itself. And that's equal to, subtract this out. So again, limit delta x2 tends to 0 of change in x2 and change in x1. And at this stage, you would say that, oh, this doesn't mean anything because x2 is independent of x1. It is not a ratio of two numbers. It would be a ratio of two numbers if x2 did depend on x1. But this doesn't depend on that change at all. So this is not a ratio. So this is equal to delta 2, 1. Is 2 and 1 the same variables or not? This is equal to delta 2, 1. If 2 was the same as 1, then that is equal to 1. Otherwise, it is 0. That's what I meant by that. Does that clarify a little bit?
Yes, very much. Thank you.
Be critical about that because it's a notation, right? And I'm trying to build something very quickly. I'm going to make this continuous, and there will be confusions with this notation.
Thank you so much.
Yeah. Harsha, is this clear? Oh, we lost Harsha. Harsha? Okay. So
Oh yeah, it's clear. I was muted. I didn't see.
Oh, okay. Yeah. Is it was it clear, the notation? The slide.
Yeah. They're just rectilinear coordinates, right? So they're independent of each other.
Yes, exactly. So that's rectilinear coordinate, but I'm stressing some notation here. Notice partial derivative of x1 with x2. That's 0, of course. That's all I'm emphasizing. But I'm doing this as a variation. Right? Delta x is being thought of as a variation in that parameter.
Yeah. Okay. So if the coordinates were not independent, then you'd have to use what I mean.
You have to take a derivative.
Yeah, the function, how you did it, the limit sort of thing.
Exactly. Okay. So with that, let's now do the actual thing that we are interested in doing. And let me erase this so that I have more space. I already erased part of it. Okay. Notice again, let's have it. So think of this as an example, right? So f of x, number was a dotted with x, which was a of I xi, a1, x1. Think of I as being continuous for some reason, and instead of f as a function of x, now I'm going to define this is a functional. Instead of a curly parenthesis, I'm going to use square brackets. That usually represents that this is a function of a function, not in the spirit of a function being a function like, for example, sine of cosine of x. That's a function of a function, but here it's a functional in the sense it could be any function. So what does that mean, right? So this is u, which is a function now. You typically don't write it the variable is not shown there because we are going to integrate this. So this is called a function. Not a function, it's functional, right? So simple, one of the simplest functional you can think of is, let's go from a to b, and this is an integral dx, and in the same spirit as we did there, notice this is a of x, and now there is a u, so this is u of x. Actually, maybe just to give a better picture, let me change that variable there and call that u. U could be a vector. Right? So this is u and ui. That makes the convention better. Right? Notice u has 3 components in here, which shows up as u1, u2, u3. Here, u has infinite components in the sense that it's a function of x and you're summing over. So this is a summation, right? So this is summation of I going from 1 to 3, A, I, U, I. This is a summation, but summation over a continuous variable, which is an integral. You see the similarity in the two, or analogy between the two. You're basically, instead of discrete sum, we are going into a continuous sum. Okay. And now that's our functional. So what is U now? U could be any function, right? This is a, I don't specify what that U is. It could be sine of x, cosine of x, any function you want to imagine in that region. That's what the pictorial diagram. If this was x, and this is U of x, so this is A, and that's B, right? And if you're, in principle, I don't even have to specify this U of A, but for a moment, let's say if U of A and U of B was fixed, then it will always start from here and end there. But in general, so this is any function going from this to this, right? So these are all examples of U. And now you can ask, since I'm having a function of U, if I say, oh, what is a minimal piece out there, then I have to minimize this quantity and try to do something with it. But that's what we did there, right? We took a derivative with respect to 3 coordinates there. I would like to find a derivative with respect to a function. Not a derivative with respect to a variable now, derivative with respect to a function. Here, there was a derivative with respect to U, which had 3 components. In that spirit, this is going to be a derivative with respect to U, which has infinite components in the sense that it's an integration over x. Okay, so functional derivative now would be, so this is the f over delta U, and this will be limit the change in f divided by change in U, and the limit of delta U tends to 0. So that means to say I'm going to change the, out of all possible functions, I'm going to change the function a little. So that's equal to, this is the same as limit delta U tends to 0 of the functional U plus delta U minus of f of U divided by, this is U plus delta U, and I have to actually at this point specify the quantity. So yeah, I should be more careful. Right? When I say delta U, I return it as a variable, right? This is a function, so at this point I have to bring in the functional value. So that's your x, and I should also clarify this here. That's delta U of x. But on the top, you don't write U because that's a definite integral, right? This does not depend on x, so there is no point in writing the x there, because a definite integral does not have any x dependence. But the moment I take a derivative, it is an x-dependent quantity. So this whole thing will be an x-dependent quantity. So if you want, so this is at this stage still, the moment it's functional, it's not a function of x. And here you can say U plus delta U and minus U. So this is U of x plus delta U of x minus of U of x, like we did earlier, but these always cancel out, right? So divided by delta U. So that's the way I want to define that. And U again, we want to imagine that to have all possible functions, but then you pick a variation in there. Okay, so now what is that equal to? So this is limit again. Limit, this was again x, right? Delta U of x tends to 0, and there is denominator, so I'll bring that out. So that's delta u of x. And f of u, what is that? F of u plus, I'm making a u plus delta u. So this is integral of a to b dx times a of x. But let's be careful. I already used x as an independent variable, so this integral has to be x prime. Exactly like here, right? If I'm doing a derivative with respect to I cannot use the same I that I used in the summation, right? That's a dummy variable. Same thing here, so this is x prime. And this is a of, so this is u, let me say this is u of x prime plus delta u of x prime. Minus, am I still within the board? Yes. And minus of the original, so this is a to b dx prime, a of x prime, u of x prime. Any questions at this stage?
Real quick, the f of u plus del u at the top of that denominator. Yeah, those aren't function u's, right? You're saying that those are the vector u's?
Vector use, I don't understand.
At the top, I just am kind of confused on the notation because you have u as a vector at the very, very top, and then you have.
Oh, yeah. Here, okay, this u and this u is different. This is an analogy. So this is a big leap you're making.
Oh, understood. Understood.
Right, so this is a function of x. This is a 3 variable property. Okay, that's an analogy. Did I answer your question or?
Yes, thank you.
Okay. Any other questions? Because it's mostly notation, otherwise, and of course there is a, like you're making a big leap here in the sense of discrete to continuous. So surely it's a little sloppy in that sense. Okay, so stick on, just keep with me. Now notice that the first piece here, so I'm going to explicitly, let's write this. Okay? So this is, let me write this as just for clarity. So I'll write this as 3. This is delta u of x tends to 0, 1 over delta u of x. And this is a to b dx prime, a of x prime, u of x prime. Like remember our first example in the limits, derivative as a limit, if you want. This is dx prime, a of x prime, and this is delta u of x prime. That's your change, and the original piece always sits, and you are subtracting, that always shows up. And this was a simple example, so the change was, this was the only change that came up, but in general, you could have more terms in there. And these will always cancel out. Like that's the idea of derivative, that the first term will always cancel out before you take the limit. If you take the limit, then there is an infinity there. This is a very small quantity, small change. So that could be not defined. But this, before you take the limit, that always cancels out. And let's see what you do. So now that's equivalent to limit. And this is a change, right? So change in the function. This this is not just a variable change, that's a change in the function. So that's delta u of x, and that is an integral a to b x prime A of x prime delta u of x prime. Correct. This is an integral in x prime, and the coefficient that is sitting in there, that's a function, it's a change in the function if you want. So there was a u of x, and you made a small change in it if you want. That's how it could be. So that difference between the changed function and the original function, that's your delta u of x. That's a number at each x there, but it's a function of x. But this is an integral on x prime, so I can actually take it in. Right? So that's one big step. So you do. So am I still in the boat? I think so. So that's dx prime a to be a of x prime, and you say this is delta u of x tends to 0, and say this is delta u of x prime, and this is delta u of x. I can do this because if this integral is not dependent on function of x. This whole piece. This should be compared with what we did earlier. Delta of xi over delta of xj. We at that time said this was a canonical delta. Right? If I is independent of j, that's 1, otherwise it's 0. Here what is happening is, remember your Snell's law example we were doing, so we did this stratified mediums, right? So this keeps going, and the way we were trying to do this, we made a small change there. So this we said is y1, let's say, and that was a y2, and that was a y3. And we asked the question that if I were to take a derivative, find the function for which the change with respect to y1 is 0, find the function with respect to y2 is 0, and so on. Right? That makes y1, y2, y3 all independent of each other. And that's what this means. This is a variation. So this is y1 will be variation of u at point x prime, and this is a change in the variation at point x. So we said that y1 and y2 is independent there, right? So exactly like partial derivative when we were doing for this vector function, we said u1 is independent of u2. So here we are going to say that these variations at x and variation at x prime is independent of each other. So we are going to make a big claim here that, or what are we requiring is delta of u of x tends to 0 of delta of u of x prime of delta of u of x is equal to 0 if x is not equal to x prime, and I have to now write, earlier we had delta ij, right? So this was equal to 1 if x was equal to x prime. That's okay, but here we are not going to write 1. Okay? So we're going to say that this is going to be equal to infinity when x is equal to x prime. And why is that? Because when I want to add up, so this is when I add up all these quantities with a change in x, I should get at least one place where it is 1. And if it was 1, then when I'm doing an integral, that is still 0. This is the idea of a delta function. That's because I would like this to be in such a way that when I go from dx, this whole piece, if you want. So let me write that. Limit delta of u of x going to 0 of delta of u of x prime over delta of u of x. But when I go as an integral, it doesn't matter whether it is prime or x, let's say, since we did the integral in x prime there, so let's say x prime, and going from a to b. This I would like it to be 1. I require that. And if you want that to be 1, since this is a really tiny element there, like small element, this is 0 multiplied by something has to be equal to 1. Somewhere it contributes. Only at one point it contributes. So then that has to be infinity. Not any kind of infinity. So you want to think that that infinity is not well defined, but that's such an infinity that it actually has to exactly cancel this. So delta function is not just infinity in any sense. It is actually an infinity that is linear in x, in the sense that integral of delta function is equal to 1. So that's one big leap or step I took from that. But if you allow me to do that, right, with that, now ask you guys if this makes sense again. So this is dx prime, but if you allow me to do that, a of x prime, this is actually a delta function, x minus x prime. And once that's a delta function has this property that whatever this is, this will evaluate at x, right? If assuming that x is in between a and b. Right? So this is a of x. Like remember, if you had a derivative, you would have got a vector a, right? If it was 3 variable discrete gradient, you would have got a vector a. You would have got a vector a, which was ai, right? But instead of ai now, the I is continuous, so it's an x. So if you want, you can think of it as a vector a of x in that analogy. Questions? Should have a lot of questions. Is that bothering?
You said that was the analogy, was what was under that limit right there. I kind of missed that, unfortunately.
Oh, so what I was trying to say is that this should be compared with, okay, maybe go on the right side. So the point was, earlier we said f of u, right? So f of, I had earlier said f of x, but this is f of u. This is u1, u2, u3. Is that clear? This is not u of x. If this was a dotted with u, then the gradient of f is equal to vector a. Here, u is equal to u of I, if you want, and this is u1, u2, u3. So there are only 3 components for this. Right? Now I'm saying, in the same spirit, f of u, and this is, instead of a summation over u, I'm doing an integral over u. So this is a of x and u of x. And I'm going from a to b. This could be a little confusing. This a has nothing to do with this a. Okay? Bad notations. I'm just coming up with this variables. Is that, hopefully that's not a confusion. And b, okay. And now I'm saying a functional derivative of f, this gradient should be thought of as with respect to u of x. That is equivalent to saying this is a gradient derivative of f with respect to x, let's say I. So this is xj. Usually you don't write that u, right? So this is u. Okay. So this is with respect to ui, sorry. ui. So there is so this I is that I here, and instead of I, now it's continuous, so that's x. So this comes out to be equal to exactly a of x. That is, this goes away. You think of it as a normal derivative, this goes away, and then you just have a of x. So that was the analogy I was making. So earlier we had a vector a, now we have a If you think
I
of a
see.
function as a vector with infinite components, that's what is happening.
Okay.
Like, is that analogy clear?
Yes.
Harsha, any questions? Is that clear?
Yeah, it's clear.
Okay. So with that as our defining property of a functional derivative, let's do a couple of examples. But as we do examples, the main feature will be this. We're going to take a derivative, take this all the way to this, and use the delta function property. Okay? So let's do an example. Let's have a similar example as we did for vectors. And eventually we want to be able to use this to minimize a quantity. But let's have our functional now, f of u, that u is a function, to be equal to a square root of, yeah, I think it's okay. Yeah, so that's it. So this is a to b df, right? And let's say this is square root of 1 plus a of x times u of x. It's slightly different from what we did for the vectors, in the sense that there the summation was right here, so right sitting here. But the summation is slightly outside, but it still goes through, I think. Get the analogy. There is an analogy to a certain extent. Okay, so let's do this. How would you go about doing this? We will very quickly start doing this as if we were doing partial derivatives, but let me go in detail for a moment. So I would like to do functional derivative of f with respect to u of change in x, right? So that's going to be our notation, and there is a limiting condition here, right? So let me write that limit delta u tends to 0. Very quickly, we will stop writing this also. It will be understood that that's what we mean. Okay. So that's equal to limit delta u of x tends to 0, 1 over delta u of x. And this is a whole series if you want. So this is a to b dx 1 plus a of x, and the change in a of x, so this is u of x plus delta u of x. Right? That's where you make the change. So this was an original function. You made a small change in the function, where everywhere in x, not just at one point in x, minus of a to b of dx 1 plus a of x u of x. Okay, that's your definition. Make a series expansion in here. This is equal to limit delta u of x going to 0, 1 over delta u of x. And let me go a little quick, so that since we have only 5 minutes. So this is a to b dx. I have 1 plus a of x times u of x. I take that common outside, and whatever is remaining then is I have 1 plus a of x times delta u of x. But I already took this whole thing common outside, so this is divided by 1 plus a of x u of x. Right. So maybe like this is 1 plus. And this whole thing has been already taken out, so this is minus 1. Did I do this correct? No, there's a square root also, right? Okay, is that right? Any questions there? Okay. So if you, at this point, this is how you will take a standard derivative also, right? You will always come across a function, expand it in for small delta u, assuming that the change in this function is small compared to everything else. And in that, with that understanding, you can expand it. Delta u of x, a to b dx, 1 plus a of x, u of x. Expansion of 1 plus x, right? 1 square root of 1 plus delta, let us say. For small delta is 1 plus 1 by 2 delta, right? Plus higher terms. So with that, I have 1 plus 1 by 2 of this whole quantity is small, we are saying. So that's a of x, delta u of x of 1 plus a of x, u of x. There are higher terms, so this is minus 1 plus higher terms. Is that notation clear? I mean, this is higher terms, that this is a square of it. When I expand square root of something, there are higher terms sitting in there. But all the higher terms will go to 0 because there will be at least a delta u square in that. Divide by the small limit, that will all go to 0. But before that, before we take that limit, the first term always cancels out. So this is almost like taking the chain rule. We will later on we won't do all these things. We will actually start taking chain rule in there. Or this is 1 over delta u of x, and this is a to b dx. There is in the numerator there is 1 plus ax, in the denominator there is a factor of 1, so 1 minus 1 by 2 comes in. So this is 1 by 2 of a of x divided by square root of 1 plus a of x, u of x. And that is delta u of x. Oh, I should be careful. Oh. There is something you could have objected right away. There is this x in here, and that's an independent variable. So I shouldn't be using x for a dummy variable. So all the x's should be x primes. Same thing that we do in index notations, right? We don't use if there is an independent index, then you don't use it for a dummy one. So this is dummy. So change all that to prime. Sorry about that. And this is all x prime then. At this stage, I take this inside. So that is the similarity from this point on. Oh, or was I? Yeah, I think I was. Yeah. I had gone beyond the board space. Okay, so that's equal to a to b dx prime 1 by 2 a of x prime over 1 plus. So most of the things now will be the same, and this is limit delta u of x going to 0 of delta of u of x prime over delta u of x. But that we know is delta function. So this is a delta function. A, B, x prime, 1 by 2, A of x prime over 1 plus square root, and this is delta of x minus x prime. Because the change in u at point x is assumed to be completely independent of the change in u with respect to x prime. And delta function is the easiest integral you can do. What you do is whatever is the integrand other than the delta function, change all x prime with x. Right? Change all x prime with x. That's what delta function is saying. So that's equal to 1 by 2. Change all x prime with x and forget the integral. Right? So that's 1 plus a of x, u of x. That's it. That's a functional derivative. I already crossed the time, but if you give me 2 more minutes, so this is a functional derivative of u with respect to u as a function of x. It will be a function of x. Now this is no more a functional, this is a function now. Right? This is a function of x. Notice what you could have done all the way, right away, is the following, right? So this is a to b, the x prime, let's say, and this is square root of 1 plus a of x prime, u of x prime. If you have to do the a functional derivative, pretend that this integration is not there, this integral is not there. Do this square root function as if you're doing normal derivative, right? What you would do is, you would do, this is 1 by 2, square root of 1 plus a of x, u of x, right? So notice I changed x prime to x. And after that, I have to differentiate the argument. And when I'm differentiating the argument, if the function u shows up, I treat that as a single variable, and whatever is in front, treat that as a simple function or a simple variable and replace x with x prime. And that will be a of x. That's how always it works. Sometimes what will happen is that there will be derivatives there, and then you have to be a little more careful, and we will try to do that. But as far as you're not encountering derivatives, like in your homework, there are a few examples where derivative shows up. Actually, the first example itself has derivative in it. But as far as you're not having derivatives, this is the idea goes through, and this is only a detailed structure in there. Whenever you're confused, go through the details. Otherwise, it will go through. And as we will see, when you're doing more and more examples, you will be able to do this. Hopefully, you will be able to do this smoothly and efficiently. Okay. Questions?
Real quick, the functional derivative. What we did was just kind of prove how you would take that derivative, very similar to before with regular partial derivatives, right?
That's correct.
Okay, I'm just making sure.
That's correct. Yeah, there is a one-to-one analogy between partial derivatives of discrete variables and the functional derivative. Yeah.
Thank you.
Most of the time, unless or at least whatever we do in this course, there will be a one-to-one correspondence. Now you can have some non-trivial situation in a non-trivial system, but we will be dealing with a simple system where these things go through smoothly. Okay. So let me not make bigger claims.
Thank you.
Yeah. Any other questions?
Oh, I'm sorry, one more. I noticed that there was no quiz that you kind of you didn't give a quiz, I don't think.
Yes, there was no quiz. Yeah, what do I do? How about that? I should have a quiz. Read up wiki article on functional derivative and write a few things. why I say that is that functional derivative is usually not taught at this level, especially for whatever I'm going to do. So I want you to have a feel for how functional derivative is done in the actual literature and how minimization is done also. So look up what functional derivative is in the literature instead of just following me here, right? So that you're aware of the difference. So the quiz is, right, look up functional derivative. Just read the wiki article, and that too, don't read the full thing. Just go through it roughly and see if there is any similarity. Okay?
Okay, thank you.
I myself have not looked into the wiki article, I think. Yeah. Thank you. Yeah, that helps. Yeah, so that we have this consistent quiz going on. Yeah. Good. Anything else? Questions? And in the last class, there was a question at the end, Harsha asked, which I did not answer. We'll come to that in one or two classes. I think that will come up another. Okay.
The minimization of time, right? For
yes, minimization of time, and you were asking what happens to you. Are there more than one solution?
oh yeah, I remember. Yeah.
So hopefully we can address that and everything goes through. That's, I think it's some detail. It doesn't show up in this derivatives. It is some details of the formalism of the problem itself. Yeah. So hopefully I'll answer that. Okay, thank you. Anything else? If not, let's stop. I'm sorry, about 10 minutes extra here. If you have a class, you still have 1 minute to change your Zoom room.
I don't have a class after this.
I was trying to emphasize that if you're changing a class, these days it takes only 1 minute, right? Earlier you had to walk from one classroom to the other classroom.
No excuses.
No, that was not the reason why I extended. I try not to extend. Yeah, sorry for that. Good. Okay, enjoy, guys. Yeah, thank you.
Goodbye.
Bye.